The super business comes from a network that Caitlin Buck organised through the Leverhulme Trust, and it's a useful acronym for various things. And before we start, I just give you an advertisement. Next year in Dublin, ISI World Statistics Congress, and a couple of this is information. If anybody wants to talk to me, turn on the mic.
Please.
Okay. All right. Yeah, we're being recorded. Is everybody okay with volume? Yeah. So if anybody wants to talk to me about that. So I thought I'd just start with something quite concrete. I'm focused in the palaeo-climate, and in particular in this context I'm thinking about the climate at a particular place in Ireland on the basis of some data. We're talking about the climate for the last, say, 14,000 years. For some of you who know the palaeo-climate, broadly speaking, in some sense, the end of the last ice age was about this point. This was preceded by a period that the palaeo-climate community referred to as the Younger Dryas. And both in and out of the Younger Dryas, there was there's much evidence of very rapid climate change, And I'm going to be talking a little bit about an aspect of rapid climate change, and I'm going to make claims such as this, and I'll talk a little bit about such claims and what's the basis for making such claims and so forth. I hang out with people who work with pollen as the basis for paleoclimate study, and pollen is, the advantage of pollen is that there's a lot of it. The disadvantage of pollen is that the signal is rather weak, and there are several difficulties with interpreting the signal. And so interpreting the signal in this sort of statement, and I'll come back to it shortly, is in some sense a little bit surprising. There's some issues there of, if you like, a temporal resolution that's involved. And you'll see as we go through this that there are a lot of challenges with regard to uncertainty in all of this. And again, just for those of you who don't know very much about the paleoclimate, this is an oxygen isotope from Greenland, the so-called GIST series. I'm using a median smooth here just to tell the story, just to set the scene. This is the last 100,000 years, as we know from studying the ice, oxygen isotope in ice, and there have been a lot of changes. And in particular, the IPCC report said that during the last glacial period, abrupt regional warmings, probably up to 16 degrees within decades over Greenland, occurred repeatedly over the North Atlantic. 16 degrees within decades is rapid. And in a broad sense, some of us are concerned, obviously, and some people are concerned, I think, about the past, but many of you guys who are modeling the future, ultimately, many of you are sort of thinking about abrupt possibilities for abrupt change in the future. And certainly, looking at abrupt change is a very challenging, it challenges all sorts of things. And so abrupt change I'm using as a sort of a vehicle to challenge things. I'm going to pose a question, so what's the probability of abrupt climate change in a broad sense? Now, other people are concerned with the mechanics of this. How could this possibly happen? How could you get a change in 1 or 2 decades of that magnitude? How physically could it happen? Ocean dynamics and ice dynamics and things, and so some of you are concerned with the mechanics of how these things could possibly happen. And I'm posing a sort of a rhetorical question here. What's the probability of abrupt climate change? So the first thing is really just to make some statements. One of the things that I find as a statistician is how how difficult it is to get an agreed definition of climate. And by and large, if one asks climatologists what is climate, there is not a very well, I don't get a stock answer. I get very loose ad hoc statements of, climate is long run weather. What does that mean? What is weather? What is long run? I get very loose statements. And from my personal point of view, climate is an intellectual construct. It's an abstract thing. It cannot be measured as such. All measurements on climate are indirect, incomplete, with some error. There's issues that in statistics and spatial statistics in particular, people talk about regionalized. That is to say, every climate measurement is in some sense an average over some time and space. What is the support? What is the magnitude of that time? What is the magnitude of that? And the reason I focus a little bit on such definitions is because if I'm going to talk about uncertainty, and if I'm going to use probability as a basis for talking about uncertainty, I'm going to need to make statements about the probability of an event. And if I'm going to make the probability of an event, then that event has to be very defined. And so the first difficulty with what's the probability of abrupt climate change is what on earth do you mean by abrupt climate change? The actual very definition is, so in my work, I treat climate as a latent space-time stochastic process. It's a construct that we use. And we have measurements on this thing, but it is a construct. And so that's sort of my philosophy in this. And some of you may wish to, we may wish to come back to that. Do we need to be very formal like this, for example? Is it necessary? And for those of you who don't know very much about, pollen and proxies and things, a lot of these things come from, there are scientists who go out there and collect data. And anybody who's been out with any scientist and collect data just knows how noisy that data is and how many terrible things can happen to the data collection process and so on. And those of you who know a little bit about this know that broadly speaking, in very simple terms, pollen, the vegetation responds to the climate, and vegetation generates what they call pollen rain, and some of the pollen rain finishes up in lakes, and some of that finishes up in sediment, and some of it can be found in sediment, 15 or 20,000 years later, and so on. So that's really just sort of background. But the data, if you like, from the time it gets to me, is things like multivariate counts. So from my point of view, this is a data set which has multivariate counts in it. And from a statistical point of view, it's a data set which is a bunch of multivariate counts. And again, for those of you who don't know very much about this is a typical sort of thing that this is in Glendalough, and Glendalough is this particular place in Ireland. Core is about 15 meters deep. It covers, crudely speaking, the last 15,000 years. The horizontal lines refer to the relative frequency of various taxa. This is hazel, for example. This is ulmus. Ulmus is alder, possibly. And these are, and if you actually look down this record, you will see that this composition changes rather dramatically about here. And where is here? Well, here is about 11.5 meters down. So about 11.5 meters down, this composition changes rather dramatically. And whereas previously there was a lot of this stuff, now there is not very much of it. And whereas previously there was no hazel, now there is quite a lot of hazel. And when did this happen? It happened 11.5 meters ago. Now, how do we know how long 11.5 meters ago is? Because there's more data in this particular case. Radiocarbon dating is the basis for this. And radiocarbon dating, in this case, they dated 5 of these. There were basically 150 slices here, and 5 of them were sent off for radiocarbon dating. Radiocarbon dating is quite expensive. That's why they only sent off 5. If they could afford to, they'd probably send off a few more. There were 5 of these were dated. what is the relationship between depth and date? Well, you go to the lab will tell you, 11.5 meters corresponds to 9,150 radiocarbon years before present. What's a radiocarbon year? And they don't even say that, they say plus or minus 50. So what's a radiocarbon year, and how does a radiocarbon year map itself into an actual calendar year? And so these are the sorts of data that one finishes up with, and these data contain all sorts of aspects that normal data contain. They contain all sorts of complicated things that don't make it easy. So these are the sort of data that I start with in my work. And specifically in this case, there were about 150 slices, regular. The 28 taxa, that people can stare down the microscope and identify 28 different types of taxa. In this case, not species, taxa. Many of the counts were zero. Really large, sort of 35% of all the counts were precisely zero. 14C, we have 5 dates. As I'll show you in a minute, the worst uncertainties associated with those are the order of plus or minus 2,000 years. So if there's uncertainties of plus or minus 2,000 years, how can you make statements, pertaining to what happened in 100 years, or how can you discuss abrupt change in these sorts of contexts? I use some data from Greenland that I mentioned previously, and some of you will know more about this data, and I use this to discuss what I call climate smoothness. Now, modeling issues, so I'm going to be talking about statistical modeling. When I use the word model, I mean a statistical model. Some of us were discussing earlier that people have different views of what the word model is. From my point of view, a model is a statistical model. A model, therefore, is a stochastic model. A model, therefore, has an explicit mechanism for randomness involved in it. If it doesn't have some mechanism for randomness involved in the model, it's not a statistical model. So I'm using modeling, and I'm going to be talking about sedimentation, for example. Sedimentation is a process. Now, sedimentation is a process that is a non-decreasing process. Climate is a process that is smooth, well, sort of, or almost everywhere. What do we mean by smooth? Vegetation responds smoothly to climate change. What do we mean by smooth? There's data generating process. There are priors and there are algorithms and things of this sort. I'm not going to talk very much about the algorithms, well, except conceptually. The algorithms are essentially Monte Carlo. I'll be displaying them to you with pictures. But the key thing here is there are sort of modeling issues. What is climate? How do we model these things? What is a statistical model? What is uncertainty? These are the sorts of questions that we're talking a little bit about. And this super thing is, there's a paper that some of you will know a little bit about, and one of the objectives of the exercise is to finish this paper here. And in principle, we're aspiring to modeling all sources of uncertainty. We're aspiring to issues of communication. How do you communicate uncertainty? How do you communicate uncertainty to the public? How do you communicate uncertainty to each other? And I want to make some remarks, perhaps. I know the Exeter workshop is very much concerned with data sets. And at that workshop, there'll be issues of how do we communicate uncertainty to each other. So these are the sorts of things that are on the agenda. And so the modeling approach, in terms of actually how to make this operational, we adopt latent processes, which are latent stochastic processes. And these latent stochastic processes have defined stochastic properties, and I'll talk a little bit about some of them, and they involve explicit priors. And then conditional on those, we model the data generating processes. So for example, there's a process that ultimately leads to multivariate counts in my computer. And that process starts with the vegetation, but it includes the scientists who are collecting the data and the scientists who are staring down the microscope and things of that sort. We combine all these things, using conditional independence. and we build a joint model of an entire system. With this is an approach. And then to make this manageable in practice, we aspire to some sort of modular approach to this, and I'll define something. And ultimately, the output is very much driven by Monte Carlo, and the output is what some people in this world call ensembles, and which I might prefer to call a sample path. And then subsequently, there are marginalization to well-defined random variables and events. So that's how to make the thing, as it were, practical. So as much as anything, I'm going to use a practical example, but the objective of the exercise is to think a little bit more about what it is we're up to when we talk about uncertainty in abrupt climate change. And we're sort of piggybacking really on a lot of stuff that's been happening in statistics over the last 20 years with regard to modeling statistical models, partially observed space-time stochastic processes, Bayesian inference. There's been a lot of work on all of these sorts of things, on Monte Carlo algorithms. And there's a lot of stuff that's been happening in the statistics community over the last 20 years. And several people here are very interested in specific aspects of that. And this is now becoming available to us. And so I put the word modeling uncertainty. How do you know if you have modeled uncertainty? So many of you, I think, will have paid some attention to uncertainty in your work. But how do you know if you've modeled uncertainty? And I suggest a sort of a litmus test as to whether you have modeled uncertainty. Does your uncertainty change in space and time? Is your uncertainty just one number? If your uncertainty is one number plus or minus something, I suspect you haven't really modeled it. Your uncertainty changes with the amount of data. It changes in space, it changes in time, it changes depending on what you're talking about. And if those of you who have been dealing with uncertainty or reading papers that deal with uncertainty, and if somebody says uncertainty is plus or minus 3, period, I suspect that the uncertainty has not been modeled. Some of you may wish to challenge me on that later. So specifically in this context, I aspire to a situation where we have multiple proxies, typically in cores. In my case, I'm only going to work with one proxy and one core. But there are multiple proxies and multiple cores in multiple locations. Typically, the depths are known, but the dates are not. And there's issues of calibration, calibrating the dates and calibrating the signal that comes from pollen and what it means for climate. There's some sort of system theory in here. There's a thing called the uniformitarian hypothesis, which is actually a really rather crucial hypothesis. The uniformitarian hypothesis says that in some sense if we want to make statements about the past climate, we can base that on theory, which is concerned with the present climate. So we can learn everything we need to know about climate by studying the present climate, and we can use that as a basis for making statements about the past. The present is a model for the past, and that's a theory. And clearly, it's an approximation. And issues, for example, are would vegetation have changed had CO2 levels been quite different? Or had mankind not been down there even 5,000 years ago? We're talking about climate smoothness and sedimentation rates and proxy data generating processes. So now what I'm going to do is I'm going to deal a little bit explicitly by way of pictures with one module. And one module is concerned with chronological uncertainty, the dating uncertainty. But the dating uncertainty is just one aspect of many things, but I'm going to focus a little bit on the dating uncertainty because it's sort of a very clean example with which to communicate the sorts of things that we actually do. So I'm going to look at sedimentation. So how do I know that stuff that deeper is older? Because sedimentation has been building up. And one of the things about sedimentation is that it builds up, it doesn't build down. Sedimentation is a monotone process. I'm going to model it as rates that are non-negative. The rate of sedimentation is non-negative. The rates are going to be piecewise constant. The implication of that is depth versus time is a stochastic process that is piecewise linear.
But it can erode as well, can't it, sediment? Sediments can erode.
Yes, yeah. I mean, again, there's a model here, and in principle, we can add things onto it later on, and you're quite right. You know, all modeling statements are, of course, approximations, and the question is whether the model permits, development in some sense. You're quite right. Yeah, there are all sorts of things can happen. I'm going to look at random change points in this according to some Poisson process. I'm going to talk about random variation in the rates, which are to do with a gamma distribution. And I'm going to define a latent process that has properties like this. And I'm going to use that latent process that properties like this as a vehicle. Now, radiocarbon calibration curve, that's a latent process, as well. It used to be thought that 14C equals calendar date, and then it used to be thought that 14C is a linear function of calibration, and then it was thought that 14C is or calendar date. Then it was thought that 14C is perhaps a monotone function of calendar date, and now it's recognized that 14C isn't actually even a monotone function of calendar age. I'm going to treat it as smooth. It's a latent process, and I'm going to treat it as smooth. And this work has been done. This isn't my work. This is Caitlin Buck's work from years ago with regard to this. I'm going to talk about the data generation processes involving Gaussian errors. So somebody ultimately takes some of this stuff and puts it into a machine in the lab and reports something. And that laboratory process has errors. And those errors are typically reported as plus or minus something. And I'm going to say this involves a Gaussian process. So the point about this model is that the word stochastic is mentioned many places in detail. This is a stochastic process. And then ultimately I'm going to be looking at studying posteriors. I'm going to look at entire what I call depth time histories jointly. And I want to just give you sort of a feeling for one particular module. So to make it concrete, here is a monotone, piecewise linear. In our case, we call it a compound Poisson gamma process because it has some nice properties that allow us to do some things quickly. So this is, if you wish to interpolate on the unit square from 0 to 1, one way to do that is to drop a random number of points. In fact, I'm going to use a Poisson number of points in here and essentially join the dots. And these are all piecewise linear processes. They're monotone, and they have well-defined properties. And I'm going to use this as a model for sedimentation. There are some aspects of that. Let's see if we can pick those up later on. Okay, let's see how that goes. Right, okay. I thought I had a nice picture for you, and you will excuse me if I just pop out of this. And, oh, I know what's happened. This was a hidden process. Okay, so let's, so this slide has been hidden, so, right, okay, so let's get out of here and see what I can do with this. And I don't want to hide that slide. And I don't want to hide that one. Okay, so I'm going to unhide that one, I hope. Yeah, that's right, yes, exactly. And unhide this slide. Okay, so let's, I think we have to go, but I'll just page forward quickly. Okay. So this is, in some sense, one of the outputs, and we'll come back to the mechanics of this in a minute. This is an output. Remember, we had 5 dates. These are the dates. And these blue points, the dates are quite well known. in between these dates, we have to do some interpolating. The interpolation is not quite so well known. There's uncertainty in the interpolation. Do you interpolate in a linear fashion between here and there? Or do you, for example, interpolate in a piecewise linear fashion? If you interpolate in a linear fashion, there's only one line. If you interpolate in a piecewise linear fashion, there are several lines. These several lines allow us to think about uncertainty, and one aspect of the uncertainty is as measured here. So, for example, here at 13 meters down translates into somewhere between 11,500 and, dare I say, 12.8 thousand. So this depth maps into a temporal interval of length plus or minus perhaps 500 years. This one maps into an interval of, say, plus or minus 2,000 years. Where do these things come from? These things come from this stuff. So it's by doing lots of things with this that I finish up. Now, what we then do is we then have many of these paths, and if I want to determine, what is the age associated with the depth, then I can generate lots of lines. I can draw lots across and down here, and I finish up with this, and we finish up with the distribution of the age associated with this particular point, and so on. And I call this stochastic interpolation, piecewise linear stochastic interpolation. There's lots of stochastic interpolation, but this is a piecewise linear version of stochastic interpolation. But the basic idea is that there is a stochastic process model, which in this case I call a compound Poisson gamma process, which is piecewise linear, and it allows me to do things, and I'm using that as a model. So the idea from that, this one module, one aspect, chronological uncertainty. How do we study chronological uncertainty? We study chronological uncertainty by specifying a stochastic model, in this case piecewise linear, by studying the data generating process, doing Monte Carlo sampling, doing these things, and sampling entire chronologies. Okay, the next stage is how do we relate pollen to climate? Well, the people I hang out with use what they call modern training data. This is the present as a model for the past. So they have a bunch of data points that people have actually been to in recent times, where they have actually measured the climate at that point in time, and they have measured the pollen spectrum, as they call it, at that point in time. Here's a bunch of things that are in Europe. They have people I work with have about 8,000 of these things, some in Europe, some in North America, and they're used as basically a training thing. I wonder how that happens.
A transfer function between the specific assemblage and, for instance,
that's it.
the atom.
In principle, yes. In principle, you push in an assemblage and out comes a temperature. Okay. Hopefully, out comes a temperature with uncertainty, and uncertainty that you can stand over. But that's what they call it. Now, there are versions of this. A very simple version of this. This is a relatively simple version. Vincent Garretta, who's here, for example, has been studying a much more complicated approach to this with a detailed model of how the vegetation process itself evolves. It's another stochastic process with its own stochastic input and its own stochastic dynamics. In my case, we're using a very simple transfer function type approach to this. And so we basically, it's regression, if you like. It's a complicated version of regression. Now, just to point out one thing, that are probably several of you here, I was at the IMSC meeting in Edinburgh a few weeks ago, and there are a lot of people talking about proxies, and the proxies that people were dealing with typically were dendro-type proxies, and the calibration procedure with those is actually quite different. It seems to me there's one school that, if you like, has, shall we say, two time series. One is a time series on climate, much of which is missing. Another one is a time series on some proxy. And the object of the exercise is to model these as a sort of a bivariate time series, bearing in mind that quite a lot of this one is missing, and then utilizing that as a basis for sort of filling in, reconstructing. in the context of the people I work with, we use modern data as the basis for calibrating. We don't have 2 time series, we only have 1 time series, which is the past pollen. It's a time series where the unfortunate problem that the times themselves are measured with considerable uncertainty, but it is nevertheless a time series. And this, people call this a space for time substitution. So what I'm doing here is a particular version of this, but in principle exactly the same ideas apply over here. In my case, we have a model of the pollen data generating process. So the model says that the response depends smoothly on climate. What do I mean by smooth? Well, I'm using a Gaussian process to define what I mean by smooth. In my case, I'm saying there are 2 aspects to this. Climate generates both a presence-absence issue. There are some taxa that just cannot tolerate particular climates. And if they're potentially present, then there's another question of their abundance. So this is, and the way I use this is a Poisson, for example. A simple version of this is, a count is precisely 0 with 1 probability, or is Poisson with another probability. And both of these functions, this lambda function and the Q function, are both changing smoothly with climate. And we have to learn from data about the nature of these things. And but the implication of this, for example, is that a count of 0 has quite different interpretation from a count of 1. A count of 2 is rather similar to a count of 1, but a count of 1 is quite different from a count of 0 because of presence-absence issues. And this is a model. It's a non-trivial model. It's a model of a process, a data-generating process. It's not entirely just a descriptive thing. Here is a pattern that I happen to observe. I'm actually modeling a forward process. And in principle, we could build on such models, and various people, including Vincent, are doing exactly that. Now, let's move on to the sort of the final bit of this. So, what by and large happens at the moment in this literature is people do this 1 slice at a time. So, slice J, there are 150 slices. Slice 43 has a depth, and it also has a bunch of counts. And that depth maps onto age in some sense, and the counts map onto climate in some sense. And so typically, when I'm putting this now in a probabilistic terms, whence we can construct separately a statement for the climate at that particular point in time, given the pollen y, and separately another statement for the date of that sample given its depth. So these are 2 modules that are running, if you like, separately, and now we can sort of bring them together, 1 sample at a time. And if we bring them together 1 sample at a time, here's a sort of a picture that one of my collaborators has produced. I'm only here for showing 10 of 150 layers, just so you can actually see what's going on. So, for example, this represents, this blob is really 1 sample. It's giving me a very uncertain statement about what the climate was, and it's giving me some uncertainty as to what the date was. And this is another sample, and some uncertainty in the date, and quite a lot of uncertainty in the climate. Whereas if we go over here, for example, we have a relatively clean signal for the climate, but huge uncertainty with regard to the age. And there I'm just showing 10 of them, and this is now sort of superimposed. So this is in some sense now a picture of it all at once, or is it? Not quite.
What's the variable MTCO?
MTCO in this particular case is the mean temperature of the coldest month. So in this particular case, MTCO is the mean temperature of the coldest month. It's 1 dimension of climate, and of significance to botanists, because there are some taxa that it cannot tolerate minima. If they get so cold, then period, it just doesn't work. So now I've sort of superimposed all these things on top of each other to make this sort of blob. And what does this blob actually mean? Well, you might be tempted to say, well, this means that climate could have been anything in here. And that would be a very inefficient statement, because as I'll now discuss in the last part of this thing, there are many potential climate histories. You can draw lines. You can envisage sample paths that wander around in this. And many of those are, if you like, consistent with this blue blob, but they're inconsistent with climate theory. Some of them will be just involve too much rapid change. So just to make the point, so what we're actually going to do shortly is we're going to refine and going to subsample from these. But just to, and that's the last sort of module, and there's some technical stuff in that you guys can probably help me with a little bit on that. But just to make the point, here is just an artificial thing that I just created. Here's a sample path. I'm going to show you 3 or 4 sample paths, and I want you to tell me which one is unlikely. Now, you might say that a sample path like that, that's a bit unlikely. Climate doesn't do that stuff. So if I generated a sample path that was consistent with this, but in fact contained within it something like that, you might say that's a little bit unlikely. Climate doesn't do that stuff. Well, what does climate do? Okay, now, this is probably far too small for you to see, but anyway, so what have we got up here? On the left up here, I have the Greenland ice core data as sort of, published in one of these various, data sets that are available online. The bottom in black, let's see if your pointer. So the bottom in black is a measure of the, this delta 018 thing that they generate, mapped in this particular case into, no, it's actually just delta 018. And so this is if you like, a time series every 20 years for the last 10,000 years, 100,000 years of this thing, obtained by somebody who has painstakingly gone down the entire ice core and measured something and done a lot of counting and quoting and producing things and putting them into a spreadsheet and making them available to people like you and me. And this is a first difference. So if I take first differences of these, this is what I get. And if I do an autocorrelation function on this, this is what I get. The autocorrelation function is effectively flat. Those of you that are astonishingly good eyesight can see actually there is a correlation of the order of about 0.1112 or something like that. But largely speaking, there is no autocorrelation in this. A random walk is not a bad model for this. On the other hand, if you now do a probability model for these first differences, and if you plot it against a normal plot, this is not a normal distribution. So this is a long-tailed random walk. And so I see a long-tailed random walk in this series. And so I'm now making a statement here. A statistician is making a statement about climate to be, I hope, improved during the course of our time here. So I make a statement that this is a property of climate, that non-overlapping 20-year averages are such that the first differences are adequately modeled as independent, inadequately modeled by the normal distribution, adequately modeled by a long-tailed distribution. We use the normal inverse Gaussian distribution, which happens to be a rather convenient distribution for this purpose. And it has a closed form PDF. It's infinitely divisible, it's easily simulated, and can be regarded as a scale mixture of Gaussian. So this is a convenient, so sample paths are easy to generate. The sample paths that I was generating for the chronology were piecewise linear and monotone. These sample paths have increments of this sort, and they're independent. And this generates, and Hans and I have been discussing this, and Hans this generates sample paths that I think we can say are continuous, except at a countable number of points. So it's continuous almost everywhere, but discontinuous sometimes, which is a much weaker property, weaker statement of smoothness than, say, a Gaussian random walk is. So what this now boils down to is, in very crude terms, what I do is I'm going to sample from this process, and some of these things from this process are going to fit within this blue envelope, if you like, and some are going to be rejected. And ultimately, if I summarize it all, I get something like this. So now, by virtue of invoking something called climate smoothness, I actually have a very much tighter statement about climate uncertainty. But I also have something that allows for climate to change rather dramatically during the younger dryas, and it does. And down here, for example, this if you look at time slices anywhere, this isn't even strictly unimodal. So the time slice here, if I was to make a statement at 12,000 years ago, my statement about the climate at that time on the basis of these data would not actually be a unimodal statement. But then we can go on to the final thing, is we can look for rapid changes. So we can look at these sample paths, and we can inspect each sample path. In this particular case, I'm going to inspect each sample path, and I'm going to identify the 100-year period with the greatest change. And I can do this for every sample path that I have. Here's one where the greatest change was actually not at the end of the younger dryas. But mostly they were. And I can finish up with something like this. So this is the end product. And I make the statement that 95% of plausible scenarios have at least one 100-year positive change which is greater than 5 degrees. So I began the statement by saying, what's the probability of a random event, of an abrupt event? And now I'm beginning to, this is a rather more specific statement. What do we mean by abrupt? Abrupt is defined in a particular sense, but those of you, who are wide awake will be able to challenge aspects of that as being ill-defined as well. So that's the sort of the end product of this process. And so I don't expect a great deal of new science about the younger dryas to emerge from one pollen core, at one location. But I'm actually quite surprised that we finish up with something as clear as this, which is actually consistent with what is known, in fact, from other things. It's sort of quite remarkable, given the paucity of data and the quality of the data, that we can actually come up with such statements as this at all. So finally, communication. There's communication to the general public, but there's also communication scientist to scientist, and communication about uncertainty. And while I won't unfortunately be able to get to the Exeter workshop, I know that one of the things about the Exeter workshop is data sets. And therefore, associated with those data sets are two sorts of things. One is a precise statement of the support. These are regionalized variables. A precise statement for the support of these variables, and a precise statement of uncertainty. But what do I mean by a precise statement? How do I communicate a precise statement of uncertainty? I would argue that error bars are absolutely useless. Error bars make some sort of statement marginally 1 point at a time. There is uncertainty in the entire series, not in 1 point in the series. And the only way I can actually think about providing data sets for each other in a way that involves uncertainty is to provide multiple copies of the multiple ensembles, multiple possible statements, multiple possible joint statements. And I would argue that error bars is a completely pointless way of approaching that. And if you do that, we are seriously under-communicating. So the basic approach to here is that this involves latent processes, latent stochastic processes. Climate is latent. Climate is not measurable. Climate is a construct. Climate, nevertheless, has some statistical properties, and these statistical properties can be stated, at least in principle. With conditional on this latent process, we have models of a data generating system, because all the data that we ever get contains, well, it's inadequate in many ways. Measurement at the very least, but it really reflects another stochastic process that generated the data. So the data, whatever data we get, they arrive via some stochastic process and contain all sorts of noise, and combining them by using conditional independence, building a model of an entire system, and then using Monte Carlo stuff. And so marginalization to well-defined random variables, afterwards. So this is, I have here chosen to post-process my data to provide you with a nice little histogram. But it's a post-processing. What I actually do is I generate ensembles, and then these I would call them sample paths. Some people in the climate community call these ensembles, and there are some issues about that. But once you have sample paths, these sample paths are consistent with the theory nominally, and consistent with the data in a statistical sense, and are therefore the basis for moving forwards. But another aspect of this, which we haven't spoken about very much, is what exactly is the support for all this stuff that I've been talking about. If somebody has actually gone to some lake and taken a little bit of sediment, and in this little bit of sediment they have found something, what is the support for that data? Well, that pollen got into there over a period of time and reflect an area in space. How big is that area? How long in time is that area? Then they go off and they measure the climate nearby. What do they measure by the climate? What exactly is it? Perhaps, what is the support of the measurement called MTCO? Is that 30 years, 10 years, or what exactly, and what region does it refer to? Uncertainty involves support, and uncertainty involves, our data. To make this operational, you really need sort of modular things to make this operational. To make this operational, you need to get things to work at some speed. And then just to finish up with my advertisement. Thank you very much.
Can you go back to your 95% slide? I lost track of the time scale.
Say that one?
I lost track of the time scales. So,
okay.
So what are the time scales in the book?
Okay, here are the times, but first of all, let's start with this one. Time scale here is 0, which is now, and 14,000 years ago, which is here. And so this is the younger dryas that is sort of kicking in at about sort of 14 to 11,000 years, with lots of dramatic things happening to the climate. And in this particular case, lots of dramatic things happening to the vegetation. And the temporal, so that's a time scale in that sense. Now this refers, actually just I've gone through all this and picked up 100-year differences from each of my ensembles one at a time. So this involves a very different sort of time scale.
So this is a measure on sample paths in this.
This is a picture, if you like. This is a picture, if you like. This is a picture of all the possible samples. Well, not all the possible, but this is a picture of as many as I have simulated. This is a picture of as many that I've simulated, and it's useful only for one purpose. This picture is useful only for one purpose, because I can go to a particular point in time and do a slice. And that picture tells me nothing except, the only thing I can do with that picture is take a time slice at a particular point. And that tells me what my statement about the uncertainty was at that time. But this picture tells me nothing about the dynamics of individual ensembles, individual sample paths.
So can you say, I just want to see if I understand.
Yep.
Can you say 95% of plausible scenarios have at least one 100-year positive change bigger than 5 degrees Celsius
from the red thing?
More than 10,000 years ago?
Yes. Yeah, I can say, that's exactly what I can say. That's exactly what I claim to be able to say. Now, you may challenge both the details of my modeling, and you may challenge the theory upon which my modeling is based, which theory is both vegetation theory and a climate theory. And hopefully, having challenged them, we will get a better model. But what I was actually outputting are these sample paths. So if I was actually presenting this to a group of lay people, I would present this picture. If I wanted to present this to a group of scientists to actually work on, I would present them with 10,000 sample paths. And then do what you wish with these 10,000 sample paths. I would communicate my uncertainty by providing 10,000 sample paths. And with those 10,000 sample paths, some scientists could produce this, and some scientists could produce this, and other scientists would produce something else. But if I want to communicate my uncertainty to other scientists, I would not use pictures like this. These are just pretty pictures for the press or something like that. But they're not a way of communicating uncertainty in any meaningful sense to scientists.
You tested your sort of fundamental synthesis model by removing one of the carbon dated points.
Yes.
And presumably your piecewise anything still falls.
Yes, we have tested it. There is, I mean, just as we speak, you know, I have a student at home who's actually doing a whole bunch of runs with a 4 or 5 hour compound Poisson gamma thing. It's just one way of doing this. Other people have different procedures out there. And there is a student at this moment who is, you know, working over a hot keyboard, you know, trying to do hundreds and hundreds of these. But the answer is yes, we've done many, but not yet thousands and thousands. Now, if I go back to now, this statement, this picture is sort of pretty and sort of surprising, but sort of completely pointless. Because this picture does make the statement that there is, you know, plus or minus 2,000 years uncertainty with regard to the actual age of a particular sample. But if I'm studying climate change, I'm not actually interested. I'm interested in what happened between the relative age, the age difference between 2 of these samples. So I've got 2 samples which are 10 centimeters apart. And this provides me with, again, this picture is only a picture of the absolute uncertainty with regard to 1. This picture tells me nothing at all about the age, the uncertainty in the difference between 2 proximates. So the reason I can actually get halfway sensible results despite this is that climate change pertains not so much to the absolute date as to the relative dates of 2 things. And the relative dates of 2 things are much better defined than the absolute dates. On the other hand, if I wanted to combine this data set with somebody else's data set, you know, from Cambridge, for example. You know, so if I would take my Irish data set together with my Cambridge data set, put them into one joint analysis, then this absolute uncertainty is going to be really important for combining with somebody else's data. These statements of absolute uncertainty are really, really important. They really are huge. But relative uncertainty is much better defined than absolute uncertainty. See, this picture is rather misleading because the sample paths that are far more important than that picture.
It seems to me the mean temperature of the coldest months is a very different thing from what the ice core measures, because that's something more global and definitely not the coldest months, but still you infer distribution forces of one level from the other.
Yeah, well, so you're quite right. So here it is a statement. I observe that non-overlapping averages are, in the Greenland ice data, can be described by the normal inverse Gaussian and an independent random walk long tail. Can I infer from that that this would describe other aspects of climate? I am in your hands. I'm not choosing the parameter of Greenland. I'm choosing a parametric family. If I want to fit this to Greenland, I get one numerical parameter. That's one value, a best value in some sense. That might be the basis of a prior statement with regard to how this. So what I'm taking is essentially long-tailed random walk. And I'm observing long-tailed random walk in ice and saying other aspects of climate are probably adequately described by a long-tailed random walk. And some of you can help me to criticize that statement or improve that statement. But it's in some sense, this is my layman statement of climate theory, climate system theory. All you guys with your GCMs can probably give me a much better statement of that, at least in principle.
But is the choice of the parametric family invariant by the state change?
Yes. Yes is the. I mean, the normal inverse Gaussian is basically a scale mixture of Gaussians, and so the Gaussian is invariant to a scale change. And
then you mean that using this GISP, which is a very large average over a very large space, you find this family, and then it will remain the same for the local.
And this is, put it this way, I'm open to A, criticism, and more point improvement. You know, this is a stab in the dark by a statistician, and there are people here who know more about this than I do. But this is just a sort of a stab in the dark by a statistician. But what I want to do is I want somebody to tell me about how rapid, I want somebody to tell me from climate theory about how rapidly climate could change. And to tell me that in such a way that I can encapsulate that in a stochastic process. And so if somebody can tell me how rapidly climate could change, or how rapidly this particular aspect of climate could change, and this particular aspect involves, 20-year averages, or should it be 5-year averages, or and so on. But if somebody can tell me from climate theory a statement which is better than that, then I will immediately adopt it. So it's a layman's guess and open to improvement. I think we're probably sort of exhausted.
Any more questions? Just John once again.